Welcome. In this video, you will be learning everything that you need to know to write the names and the chemical formulas of the ionic compounds and their hydrates. If you fully watch the video and practice the questions given at the end of the video, you should be confident enough for this topic without making a single mistake. Let's start the topic. So let's first understand what ionic compounds are. Ionic compounds are formed by the ionic species held together through the electrostatic forces. So the ionic species that bind together, they can be positively charged species called as cations and negatively charged species called as anions. So positively charged species, they are formed by loss of electrons, and negatively charged species are formed by gain of electrons. So I have already covered everything about cations and anions in other videos shown up here in the card, so you can watch out that if you have any troubles understanding cations and anions. So cations and anions means the positively charged species and the negatively charged species, they bond together through electrostatic forces and hold each other together. This is called as ionic bond. And the compounds that are formed by the ionic bonds, where the atoms hold each other through the ionic bonds, they're called as ionic compounds. Overall, the compound will stay neutral because the charges, they balance out each other, charges on the metals and charges on the non-metals, or the charges on the positively charged species or the charges on the negatively charged species, they just balance each other out. So that's why the compound will stay neutral. For example, NaCl, common salt that is also used for cooking, called as table salt as well, is also an ionic compound, well-known ionic compound. Other than that, there are so many examples like magnesium chloride, calcium nitrate, calcium carbonate. Calcium carbonate is the one that is present in limestone. That's also called as limestone, present in marble. There are so many other ionic compounds present and used in daily life, from acids, even from bases, and so many other variety of ionic compounds are there. So in this topic, we will be learning the names and the formula writing. So I will not be focusing too much on the properties of the ionic compounds in this video. Other than that, we will also need to know what hydrates are. So we will be learning the naming and the formulas for the hydrates. So hydrates are formed when the ionic compounds, they absorb some water molecule. All right. So for example, if you leave NaCl outside in an open container, of course, even if it was a free flow salt before, NaCl is a common salt, cooking salt, table salt, that's what it's called as. So it will absorb some moisture and it will lose its free flow properties with time. After a couple hours or a couple days, you will see that it becomes lumpy and it loses the properties of like free flow properties that as it was when you bought it from the store. So that means it has absorbed some moisture content into it. How can we represent that in the formula? So I can write it NaCl and then putting a dot here, and X number of water molecules I can write. X means it can be 1, 2, 3, 4. If there was 3 molecules, I'll write 3H2O. Like here I have written calcium carbonate 3H2O means there are 3 water molecules attached. It can be 1, 2, 3 or any number of water molecules attached to NaCl. So that means now NaCl become hydrated. It has absorbed moisture content. So it's not a dry salt anymore. It's not a completely dry salt anymore. Other than that, you don't confuse the hydrates with aqueous solutions. In aqueous solutions, if we dissolve, let's say, NaCl in water, um, so NaCl is going to break down into Na positive ions and NaCl ions. So when we dissolve salt in water, it's called as aqueous solution. So aqueous solution means where the salt is getting dissolved, and of course the salt breaks down into ions. But hydrates are where the water content or the water moisture content has been absorbed by the salt only, right? So the hydrates are the molecules which include water molecules in their crystal structure. All right. So let's go deeper into how do we study and how do we write the names and the formulas of the ionic compounds and their hydrates. So here we can divide the ionic compounds into different categories that will help you to understand the proper specific do's and don'ts, what goes where. So that way you will end up writing the correct names and the formulas very confidently without making any mistakes or confusions. So first of all, We know that ionic compounds are formed up of positively and negatively charged species. Positively charged species, as I just discussed, called as cations. Negatively charged species are collectively called as anions. So positively charged species can be of three types. So if an ionic compound is given, first of all, you will see if there is a metal present on the left side, of course, or the positively charged species is a polyatomic cation, or if it is hydrogen ion. So if it is any three of these will be there, any one of these three will be there on the left side of the compound. So if it is a metal, the other thing you will specify for sure, this is very, very important. This is very important. So if the metal is present, so make sure you first of all look carefully that if this is a monovalent metal or if it is a multivalent metal. Monovalent metal, as the name says, mono means just a single, valent means valency, means the metals with only one valency possible. They are called as monovalents. For example, all group 1 elements, all group 2 elements. Group 1 elements, they are always going to show just +1 valencies. It doesn't matter what the case is. Group 2 always are going to show +2 valency, means they are going to donate just 2 electrons, whatever the situation might be. Like for example, calcium, always +2. Magnesium, always +2, right? Like that. Group 1, always +1, right? Other than that, there are many other examples like aluminum, always just +3. It is never going to be +2 or +4, right? So what I'm trying to say is the metals that can only lose one specific number of electrons, that means they only bear one valency, those are called as monovalents. The rules are very different for monovalents and multivalents. Multivalent will be the metal that can lose more than one number of electrons in different situations. For example, copper. Copper can lose one electron in some situations. It can also lose two electrons in other situations. So both are different. So it means it is showing up more than one valency. So it is multivalent. Multi means many, means more than one. Other than that, like iron can be 2 positive in certain cases. It can also donate 3 electrons, so 3 positive in some other cases. So these are multivalent. We will learn like what to do if it is like monovalent, what not to do, and what to do if it is multivalent later on, right? So we're just going to come up to that as well. So first of all, I'm just here we are just learning how to identify the given ionic compound. So positively charged species, right? If it is metal, and then you will look into if the metal given is monovalent or multivalent. All right. Next is if it is polyatomic ion. If it is polyatomic cation, cation of course means a positively charged species, right? So polyatomic ions, I'm just going to show you like what they are. So they are actually the group of atoms bearing a charge. We only have one positively charged polyatomic ion, cation, that is ammonium ion. That's it. We don't have any other polyatomic cation that you will be using here in the ionic compounds. So only the one that is possible is ammonium ion. So if ammonium ion is present, that means it is definitely ionic compound. Third category can be the hydrogen ion. If the hydrogen ion is present with any of the non-metal or with the polyatomic ion, they're actually specifically called as acid. We can name them using ionic compounds rules as well, but they are also called as acids when they release protons in water. So they have specific rules to write the names. So we will learn the names of the acids, the naming of the acids and bases in separate video. So, but still I will include a little bit about the hydrogen ion present, like how to write the names in this video too. But this actually makes a specific category called as acid. So we will cover that in the next upcoming video. So negatively charged species. Negatively charged species can be either non-metal or it can be polyatomic anion. Of course, if it is non-metal, it can be anything from the right side of the periodic table. Non-metals, right? So I have already covered in the periodic table video where the metals and the non-metals are placed in the periodic table. Non-metals are negatively charged species. Like for example, fluoride, chloride, right, oxide, oxygen with the two negative charges, and non-metal can be present. Polyatomic anion. So other thing you have to see if the negatively charged species present is polyatomic anion. So polyatomic anion, I'm just going to show you again from the list, right, in the next slide. But polyatomic anions will be something like, for example, nitrate. They are group of atoms with charges. Sulfate, right? So they have specific names, specific formulas, specific charges. So basically, broadly speaking, we can understand the ionic compounds this way. So positively charged or negatively charged. Of course, these two species will be there. So positively charged species can be either metal or polyatomic cation or hydrogen ion. If it is a metal, then this is very sure that very important that you look into whether the metal present is monovalent or multivalent, right? If it is polyatomic cation present, don't get confused with that this is nitrogen and hydrogen, and sometimes students confuse it with covalent compound, considering nitrogen is a non-metal because covalent compounds are formed with non-metals and non-metals together. Don't do this mistake. All right. Polyatomic cations, if ammonium ion is present, so NH4 is present, this is specifically an ionic compound for sure. Hydrogen ion, as I said, if it is present, and then it will be considered as an acid, but otherwise we can also write the names of the ionic compounds with hydrogen ion as well using the same rules. Negatively charged species, as I said, you will identify whether the non-metal is present or if it is polyatomic ion present, right? So now there are some specific rules. Just talk about that quickly. So if the metal is present and that one is monovalent, we don't represent anything specific about the monovalence, all right? But if it is multivalent, okay, something very important. If it is multivalent, we do use Roman letter with multivalent, all right? We will be using Roman letter for sure. We don't use Roman letter for monovalent. If you use Roman letter for monovalent, it will be considered wrong. Okay. So do's for multivalent is use Roman letter. Don't for monovalent is don't use Roman letter. All right. Don't use Roman letter for anything else. We will not use for ammonium ion. We will not use for hydrogen ion either. We'll only specify here for the multivalent ones because we need to make it clear that which valency of the ion was used, right? So whether the metal is you're losing 2 electrons or 3 electrons or 1 electron, which valency the metal is present in, because it does make a very important difference between the physical and the chemical properties of the compound. For example, if copper has lost 1 electron and makes CuCl, and if copper has lost 2 electrons and it makes CuCl2, both of these are very two different compounds and with different physical behavior, different chemical properties. The reactions will be very different, colors might different. So that's why. All right. And non-metals, as I said, the important rule that we'll keep in mind is the non-metals, when we write, we end up the name of the non-metal with oxide. So if it is fluorine, you find out fluorine, the name is going to be fluoride. Sorry, not oxide, I meant like ultimately it's ide. But if it is fluorine, we'll write fluoride, chlorine will be chloride, oxygen will be oxide, nitrogen will be nitride, like that. So non-metals name, they end up with ide. We don't change the name of if there is polyatomic anion present, so we'll just keep it as it is. If it is nitrate, keep it nitrate. If it is sulfate, keep it sulfate as it is. So this is just a quick summary here, just some touch up. So we're definitely going to go in details. Explore this periodic table to understand how to locate the monovalents and multivalents. So monovalent, so for example, this group 1, you see all of these are showing positive 1 charges. Group 2 is showing all 2 positive charges. So means to say group 1 is always going to lose 1 electron, doesn't matter what the situation is. Same way group 2 is always going to lose 2 electrons, doesn't matter what the situation is, right? No more than the 2, no less than 2. So that means group 2 are also monovalent, so they are only always going to show one particular valency. Same way scandium follows one specific valency, that is positive 3. But if you have landed to titanium, so you can see it can lose 3 electrons in certain situations. It can also lose 4 electrons in some other situations. So means it can make stable compounds either by losing 3 electrons or by losing 4 electrons. Means it is showing more than one valency. So it is showing two valencies here. That means titanium is a multivalent. So we have spotted a multivalent. So same way, we can spot more here. So vanadium is also multivalent, showing positive 4 and positive 5. Chromium, we can see positive 2, 3 positive. Manganese, 3, 4, 2, 3, 4. So three positive valencies, right? Three possible valencies, I mean. Iron can show two possible valencies, so like that. So the likewise, we have spotted some multivalence here. So titanium, vanadium, chromium, manganese, iron, cobalt, nickel, copper. But yeah, again, zinc is monovalent. All right. So monovalent will be one valency. So the multivalent will be more than one valencies. And the charges you will see on the top right corner. So you will always be able to find more than one charges. If that is the case, that means it is a multivalent. For example, copper 2 positive, copper 1 positive, multivalent. All right. So the rules are a little different. So for the multivalents, we do use Roman numerals. So, and the monovalents, we don't. So if you mess that up, that means you're getting a wrong answer. All right. So that's why it's very important to locate the correct valency of the metal. Other than that, of course, we know that the metals are on the left side of the periodic table, right? So I have already covered that in the placement of the metals and non-metals. I've already covered in the other video. So you can watch that out, the periodic table video. So you will understand the periodic table better if you have any confusions. So metals are on the left side, non-metals on the right side with the negative charges. Metals are obviously with the positive charges. All right, so here on this periodic table, this was just a quick review, but did you find polyatomic ions here on the periodic table? We cannot, right? So we can't find polyatomic ions on the periodic table. So this is the list I have for the polyatomic ions. Polyatomic ions. So first of all, we need to understand what the polyatomic ions are. Polyatomic ions are the group of atoms with the charges. So what type of atoms are there? They are always going to be non-metals. Group of non-metals with the charges on the top right corner. As the name says, poly means many. Poly, the word poly means many atoms together. Many atoms together, but of course the charge. So many atoms with the charge on the top, that's what is called as polyatomic ion. And in this list, we can see them as grouped together, the ions with the -1 charges, the ions with the -1 charge here, all these, right? All these are -1 charges. The ions with the -2 charges, ions with -3 charges, right? So the polyatomic ions list is usually provided again in the exams or in the quizzes. And you have to be very specific with the number of oxygens, because as you can see, sometimes the number of oxygen changes and the name also changes. For example, bromate, 3 oxygens is bromate, 4 oxygens is perbromate, 2 oxygen is bromide, 1 oxygen is hypobromite. In some other video, I will also cover, like, if it is not given, then how to find whether it is hypo or if it is perbromate or bromide. Basically, it's all based on the number of oxygen atoms. But if the list is given, you just need to locate the specific polyatomic ion used, to just use the name from there. If the name is given, just use the formula and the charges from here. That's it. So we can see two types of polyatomic ions, the negatively charged ions, and here one positively charged polyatomic anion, polyatomic cation. So only one you can see, ammonium ion, right? So we have a huge list of the polyatomic anions, but we have just one polyatomic cation. So wherever the polyatomic anion or cation will be used, you can just use the polyatomic ions list given to you, or you can just come here to see the charges or the formulas or the name of the specific polyatomic ion used in the compound. All right, now let's start to learn how to write the names and how to write the formulas of the ionic compounds and the hydrates. All right, so as you're familiar with all the terms required to write the chemical formulas of the ionic compounds, so these are some rules that we will follow. First rule is write the symbol and the crisscross the valencies or the charges on the positive and negative species. So first of all, as the name is given, so you will write the symbols of the element from the periodic table. Whenever we write the symbols, we always write the first letter capital and the second letter will be always lowercase letter. For example, we have to write sodium chloride. So let's say the name given is sodium chloride. So what we will do? So go to the periodic table, find the symbol for sodium. Sodium is Na, chloride is Cl. Write the charges underneath, +1 for sodium, -1 for silvers, and crisscross these charges. So we will end up 1 sodium and 1 chlorine. So the formula will be NaCl. Another example we can consider, let's say we write magnesium chloride. So the name given is magnesium chloride. The formula writing is very simple. So we'll write the name for magnesium, symbol we'll write here. So symbol is Mg. So you can locate the correct symbols from the periodic table. This is magnesium, not manganese. Manganese has Mn, magnesium is Mg. Chloride, Cl. Valency, +2 on magnesium. Chloride is -1. Crisscross. So we end up having 2 chloride ions for 1 magnesium. So then the formula should be MgCl2. So this is how it is. So first thing is write the symbols, crisscross the valency or the charges. So first rule we have followed very carefully and reduce to the simplest whole number ratio. Always ionic compounds are supposed to be reduced to the simplest whole number ratio. Let's see how to. For example, we have calcium oxide, symbol CaO, valency for calcium is +2, oxygen is -2. So when we crisscross these two, so we come up with the formula Ca2O2. Does that mean we need 2 calcium to satisfy the valency of the two for 1 oxygen? We don't need. Because each calcium atom will lose 2 electrons and each oxygen atom can gain 2 electrons. Just to make a bond, one atom for both of these is good enough. So that's why we will have to reduce these ratios. So the exact correct formula should be CaO and not Ca2O2. Let's consider another example. Let's say we have aluminum nitride. So aluminum nitride, Al, +3, valency, nitrogen, 3 negative. So when we crisscross these two, so we come up with Al3 and 3, but that's again wrong because we don't need 3 atoms of aluminum to satisfy the valency or the charge on the 1 nitrogen. We just need 1 aluminum will lose 3 electrons, 1 nitrogen will gain 3 electrons. So we will reduce the ratio, and this is the correct formula. All right. So this was very important that in the ionic compound we do reduce the chemical formula to the simplest whole number ratios. Now let's consider some example with the polyatomic ion. For example, the question says calcium nitrate. Calcium, we know that it's an element. We can find it from the periodic table. Nitrate, anything ending with ATE or ITE, you cannot find from the periodic table. ATE and ITE, eights and ites, so they are actually the polyatomic ions. So you will have to follow up the polyatomic ions list. So the formula for nitrate is NO3. So we'll just write down the formula as it is. Calcium has a valency of +2. Nitrate, again, the charge from the polyatomic list is -1. What would we do now? So we'll crisscross the charges. The formula we come up with CaNO3 twice. Twice means we need 2 of the nitrates. How do we write those 2 nitrates? By putting a bracket around the nitrates. We cannot write it like this because this will end up writing 32, right? And that's why the rule says that if the polyatomic ion is given and if it is more than 1 polyatomic ion, we always bracket and then write the subscript. So this subscript 2 will be written after we put the nitrate ions in the brackets. If there was only 1, then we don't need to put the brackets. All right. So the correct way will be write this, not like this. All right. So calcium nitrate. Another example we can consider is, let's say we have only one. How about ammonium acetate? Find out ammonium, the one, only one, if you remember, only one positively charged polyatomic ion is ammonium. So the formula is NH4. Charge is positive one. Acetate is CH3COO, because again it's ending up with ATE. That means it's a polyatomic ion. Look from the polyatomic ion list. So the formula is this, charge is -1. So we will end up writing it like NH4CH3COO. We don't need any brackets here because it was just one each, right? So we only use brackets in the polyatomic ion. If it is more than one polyatomic ion used, then make sure you do use it, right? If you don't use the brackets, means you will end up something wrong subscript. Other than that, we can also have the compounds with the multivalent metals. How would they look like? So for example, if we are given iron 3 chloride, how does it sound like? Roman numerals. As I said before, Roman numerals specify what valency of iron has been used in the compound. If it was iron 2 chloride, that means that is a different compound. It will have different properties, chemically and physically and even color wise. Even the phase it exists in, sometimes that is also different in some compounds. So they do show different properties. So that's why the valency specified here in this compound is iron 3 chloride. So I will write down the name usually the way we do, the symbol, sorry. So I'll write down the symbol as it is from the periodic table, but the valency I'm going to choose here is 3, not 2, right? Iron is multivalent, exists in both of the valencies, but here the name has specified that +3 is the valency. Chloride is -3, sorry, -1 valency. We'll just crisscross, so the formula comes out to be FeCl3. Done, right? Very simple. So when the Roman letter is given, that means if the name is given, it's very easy to spot, because if the name is given, you're writing the formula, that means the valency of the compound given is the one that you are going to use. All right, let's consider another example. For, let's say we have chromium 3 nitrate. Now this is getting a little complex. First of all, we have is chromium 3 means multivalent atom, multivalent ion is given. Other than that, we are given nitrate, that means the polyatomic ion is also given, right? So polyatomic ions, they will be just treated as normally. We don't need to do anything specific, just to look at their formulas and the charges as it is and then crisscross. So chromium +3 as the given valency is, nitrate is NO3 from the polyatomic ion list, charge is -1, so we'll crisscross. So the formula should be Cr. Again, remember, we have polyatomic ion and there is more than one polyatomic ion, so we are going to end up with 3 nitrates, right? So we'll write it in brackets. So don't forget that. So chromium 3 nitrate. Is that clear? So almost we have covered all that we need to know for the ionic compounds. We did with the metals and non-metals. We did the monovalent metals with the non-metals and with the polyatomic ions. And we also did the multivalent metals with the polyatomic ions or with the non-metals. So that's how the formulas are going to be like. So now let's talk about the formula writing of the hydrates. So definition, I've already made it clear. So hydrates are still the ionic compounds with the water content, so that they have absorbed some water molecules. So for example, the name of the hydrate is, let's say, iron 2 fluoride octa hydrate. So now one thing very important. The octa word that we see here is a prefix. So we usually use prefixes only for the covalent compounds. We don't use prefixes for the ionic compounds, but only in the hydrates we do use prefixes to represent how many water molecules has been attached, because water is not going to make a bond with the iron fluoride through ionic bond formation. It's not bonded to iron 3 fluoride through ionic bond, right? So that's why we will use prefix. Octa means 8. So as this is the list we will need to use for the prefixes, so octa means 8. That means there are 8 water molecules attached to this iron 2 fluoride. Iron 2 fluoride is no big deal now, because as we have already discussed how to write the formula of the ionic compound is just a normal ionic compound. Iron, so you look from the table, 2, that means 2 valency. Fluoride is F, means 1 valency, so we just crisscross and we'll end up having 2 of fluorides and 1 of iron. So formula generally should look like FeF2, but because here it says octahydrate, we do use a dot here, right? And we'll write the number of hydrates here. So here 8 means 8 water molecules. So hydrate represents water molecules. So how many water molecules are attached? We'll just simply write those many. If it is not specifically given, we can just write in some of the formulas you will see later on. Sometimes we do use X means unknown number of hydrates. So let's say if we didn't know how many, so we'll just write simply XH2O, right? So let's cover another example. We have copper 2 carbonate monohydrate. Copper Cu 2 positive 2 carbonate polyatomic ion, negative 2 is a charge. Monohydrate means single water molecule is attached. So as we do follow the rules, if you just follow the rules properly, so obviously don't forget we have to simplify here into the simplest whole number ratio, because otherwise you will end up having copper 2 and carbonate 2, but we'll write it as copper carbonate because 2 and 2 get simplified. So we will not write it as this. This is wrong, right? We'll write it like this, copper carbonate. All right. Monohydrate means just one water molecule. So we'll write just one water molecule. So you specify one or you don't, that's still fine. So just one water molecule is there. All right. So this is copper 2 carbonate monohydrate. Clear? So that's how we write the formulas for the hydrates. So here till here, so we have worked very much in details how to write the formulas for the different types of ionic compounds with the monovalents, with the multivalents, with the polyatomic ions, with the hydrates. All right. Now let's move on to how do we write the names for all these, right, separately. So likewise, as we have learned how to follow some rules to write the formulas if the name is given, so here now we will learn how to follow some rules if the formula is given and we are writing the name of the compound. First thing is metal is always written first when we write the name of, obviously metal is on the left side, so we'll write the name of the metal first. We don't change the name of the metal, but we do change the name of the non-metal. So if the non-metal, whatever the non-metal coming up, if it is oxygen, it will become oxide. Phosphorus will become phosphide, nitrogen, nitride, sulfur, sulfide, like that. So as I've already mentioned before, so name of the non-metal ends up with ide, but make sure we don't change the name of polyatomic anion. So if it is nitrate, it will remain nitrate. If it is nitrite, it will remain nitrite. Sulfate, sulfate, sulfite, sulfite. We don't change the ending of the polyatomic anions, but we do change the ending of the non-metals. All right. Something very interesting here is if it is hydrogen, because hydrogen does come as a metal and non-metal both. It can behave both metals and non-metals. So if it is coming on the left side of the ionic compound, that means it is acting as a metal. If it is coming on the right side of the polyatomic ion, sorry, right side of the metal, that means it is coming up as a non-metal. So then we will write hydrogen as a hydride. For example, let's say if I have LiH. So obviously lithium is a metal written on the left side. So I'll write lithium as it is. Hydrogen will turn into hydride. So lithium hydride. If I have, for example, I have aluminum Al2O3. So aluminum, we'll just write the name of the aluminum. Oxygen is oxide. So I'll write oxide, aluminum oxide. So writing the names is very easy, right? So for example, if I have KBr given, so the name will be potassium. K is potassium. Bromide. Same way if it is calcium, sorry, IUM, potassium bromide. If it is Ca, let's say sulfate. Now here is the problem. Don't write calcium, sulfur, oxygen separately. Calcium is metal. SO4 all together is a group of atoms you have spotted here. That means it is a polyatomic ion. So you will again go back to the polyatomic ions list. So this one specifically here is calcium sulfate. So we'll just get the name of SO4 from the polyatomic ions list. All right, so you just have to be a little careful with the polyatomic ions. So if you see group of atoms there, more than one atom there on the right side, so that means it is polyatomic. Even if you see more than one on the left, still it will be a polyatomic ion. So other example we can consider is, let's say, with multivalent. Now we know that iron here is a multivalent element. That means iron can be positive 2, can be positive 3. So how do we figure out what valency of iron has been used here? Iron is bonded with the 3 of the sulfur. That means iron 3. Sulfur was 2, so that's why it bonded with the 2 of the iron atoms, right? So the valency used for iron was 3. So we'll write iron 3 sulfide. Correct? We know that we can just simply crisscross here. So iron for 3 and sulfur for 2, right? If it was, let's say, a reduced compound, let's say if I say Cu2O, and let's say if I have another compound CuO, this is where sometimes students get confused. Otherwise, normally looking at here, this subscript on the non-metal actually gives you the idea like what valency of the metal was used. But if we see that this is reduced, because we know that oxygen is always -2, that means copper definitely must have been used +2. So don't end up writing copper. Don't look into here and then consider that oxygen is just 1. That means copper 1. No, because here this formula definitely it was a reduced formula because copper is -2. Oxygen is definitely -2 always, no exceptions. So if oxygen is -2, that means copper must have been +2. So in this case, we'll write copper 2 oxide. But in this case, what we'll do, because here we know that copper 2 means 2 is coming from the oxygen, and here oxygen is 1, that means it's coming from copper. They are not reduced. 1 and 2 is already a simplest ratio, right? So that means here we will write copper 1 oxide. So I hope that makes sense. So for example, if I write FeS now. So how do we know that iron 2 was used here. Why can't I write 1? Because sulfur is always -2. So definitely if I don't see 2 here with the iron, that means it must have been reduced. That means iron must have came here like as 2. So in the reduced simplest whole number ratios, wherever it has been used, so this is where we need to be a little more careful, right? So if it is FeS, means one atom of sulfur has bonded with one atom of iron. So sulfur is -2 always, we know that, right? So that means iron must have been used was +2. So the name of the compound we'll write here is iron 2 sulfide. Don't mess this up because this is always very important. The iron 2 sulfide, iron 3 sulfide, they're very two different compounds. Copper 1 oxide, copper 2 oxide, two very different compounds, right? So here in these two cases, we can see that it was already a reduced ratio. Looking, how can we judge that? We can see that from the valency of the non-metal, right? So if the valency of the non-metal has already neutralized the valency of the metal, that means the valency of metal used was the same as the non-metal. So it was already a reduced compound, so we'll use the valency very carefully. Otherwise, usually just looking at the subscript or the right corner of the bottom right corner of the non-metal will give you an idea what valency of the compound was used for the multivalent metal. All right. So now you can pause the video if you understand what we have done so far. So try writing the name of this compound, MnPO4. So just pause the video and try writing the name for this compound. Hopefully you got it right, but let's see if you got it right or not. The name of this compound should be manganese 3 phosphate. So if I explain, this is very much understandable that this phosphate is a polyatomic anion and always stays as 3 negative valency, and because we see that the overall compound is a neutral compound, and that means it must have already reduced to the simplest whole number ratio. We only see one of manganese, so the manganese that must have bonded with phosphate with the -3 should be manganese +3. Manganese exists in two valencies, manganese 3 and manganese 4. So manganese 3 must have been used here. That's why we see this is -3 balances out +3. So the valency must be +3. Another example. So this would be really great if you can try this out by yourself. MnO2. This is a little tricky one. Take your time and then figure out what formula it should be. You can pause the video. Let's see if you have done it right. So the name of this compound should be manganese 4 oxide. Now some of you might wonder, if it is 2 here, why did not look at the subscript? Why it's not manganese 2 oxide? Okay. The reason is because manganese, if it is oxygen 2, because we know that oxygen is -2. The valency of oxygen has to be -2. If it was -2, then manganese used must have been also +2. If manganese 2 positive must have been used, that means +2 and -2 must have balanced out each other, and the simplest whole number ratio should come up with MnO. If manganese 2 has been used, that means the manganese 2 positive and 2 negative of the oxygen, they must balance out each other, and because we know that the ionic compounds, they are reduced to simplest whole number ratio, so that means the final formula should have been written as MnO, but we have it here as MnO2. That means this is a reduced version. This is the simplest whole number ratio of the compound. So that means the other valency, we know that for manganese is 4. So manganese was 4. Oxygen was -2. So if we crisscross these two valencies, so it should be Mn2O4. and reduced version means the correct way to write this formula will be MnO2. So these type of compounds sometimes might confuse you, but make sure you do check out the possible valencies and see if it makes sense, right? So if the reduced ratio has been given, that means you have to be a little more careful. Always look into the charge of the, always look into the subscript of the non-metal. This will give you an idea what valency of the metal has been used. So if it was, as I'm again explaining, if it was positive 2 of the metal, so then positive 2 and a negative 2 must have balanced out each other, or you can say positive 2 and negative 2, Mn2O2 must have been reduced to MnO. So this is where it gives you a clue that no, the formula doesn't suppose, it's not supposed to be MnO, it's actually Mn2O4, right? So take care of these type of compounds. Let's consider another example, copper. Okay, so pause the video, try writing the formula for this compound. I hope you figured it out right. So it's supposed to be copper 2 sulfate. Why 2? Why not 4? You might be confused with why not 4 because SO4 altogether is a polyatomic anion and it does. So basically the negative charge on the sulfate must have been neutralized or balanced out by the positive 2 charge on the copper. So that's how we know that the valency of the copper used here must be copper 2, right? So let's do some more examples. So this is where you just have to be extra careful with the multivalent elements if there is any. So if it is a reduced whole number ratio, you just have to be a bit more careful and double check the valencies, right? Let's just do one more example. Let's say we have something like this. Can you write down the formula? So try it out. So this is NaCH3COO. So obviously you see so many atoms together and all of these sound like, okay, they are non-metals. We don't see any of the metal here, right? So, but still, as I told you before, if you see group of atoms, so it's a polyatomic ion. So CH3COO is a polyatomic ion. It's named as ethanoate. So the name of the compound should be, I hope you got it right, sodium ethanoate as it is, right? If there is any hydrogen ion present, for example, if I have HCl, as I told you before, we will be doing this later on in another video, like because HCl, HF, HBr, HNO3, they're actually considered as acids when they release the hydrogen ions in water. So naming of acids is a little different. So, but here still we can consider some example. Let's say if it is HCl, we can write it following these rules, the rules for the ionic compounds. So H means hydrogen, Cl is chloride, hydrogen and chloride, right? So like that, if it is HBr, we can write hydrogen bromide. But still, these have specific names and rules we will be covering up later in the acid bases naming video. Bases, they don't have any different rules. If you want, we can consider some example here, but later on I will also teach you how to identify bases that usually they end up with OH on the right side of the metal. So NaOH, OH is again a polyatomic ion, so we'll just simply write it as sodium hydroxide. Nothing specific, just normal rules if I'm following it right. So sodium hydroxide. If the sodium is not there, we have, let's say, NH4OH. So the name will be then, let's say we have it as NH4OH, so we'll name it as ammonium hydroxide, right? So like that. So these are all the rules to write down the names of the ionic compounds if the formula is given, all right? So in the last, we will learn how to write down the names of the hydrates if given the formula. So very simple. As I said, I've shown you before how to use the prefixes. So those prefixes are to represent how many number of water molecules are attached to any of the hydrate. So other than that, the normal rule we follow for the hydrates are just the same. So let's say if the compound given is, let's make it very complex, R1, something like this, right? And as I told you before, hydrates will have some water molecules attached to the ionic compound. So, but the rules for ionic compounds still apply the same. So the ionic compound, we are going to write the name as it is, whatever rules we have followed. So first of all, we spot here a metal. We'll figure out if it is a monovalent or a multivalent element. We know that chromium is a multivalent metal. We know that. Now we have to specify the valency using a Roman numeral. Yes. So chromium will be. So how do we figure out the valency? We'll look here into the subscript and we can see this is 1 and 3. That means it's not a reduced ratio. So chromium 3. Name of this polyatomic ion is used, so we'll write it as nitrate. Now, this is the name of this ionic compound. But we also see water molecules attached here, so we'll just write 9 for non-hydrate. Nona is a prefix. I have given you the list already for the prefixes. So non-hydrates. That's it. Chromium 3 nitrate non-hydrate. That's it. This is what is going to be the name of this compound. Other than that, if you want one more example, we can consider, let's say, cobalt. All right. So try writing the name for this compound. I hope you got it right. So the name for this compound should be, again, don't forget CO, always smaller, lowercase. So that means it's a metal, it's a cobalt, it's not oxygen here, right? So sometimes also students confuse with that. So if O is small letter on the right side, that means it's not oxygen, right? So MO, molybdenum, CO, cobalt, like that. So this is cobalt. So cobalt is again a multivalent element. So we will find out what valency of cobalt has been used here. We can see the subscripts again, 3 and 2. So that means cobalt 2. Phosphate must have been 3, of which phosphate is 3, so nothing to wonder about. So phosphate as it is. Now 6 is for hexa, so write hexa. Water, we write hydrate, so hexahydrate. All right, so cobalt 2 phosphate hexahydrate. There you go. And that is the name for this compound. All right, so that's how we have learned everything all about the ionic compounds, how to identify, and all the do's and don'ts. So now these are some practice questions for you. So here the formulas are given. So you will try writing the names for these compounds. So try following all the rules that we have done. Keep all the do's and don'ts in mind. So here for this practice, you will be just writing the name of the compounds. And here you will be writing the formulas of the compounds. So pause the video here. So try practicing, use the periodic table and the polyatomic ions list if you are given, or if you want to use it from the video, you can scroll back and forth. And then after you are done, then I have the answer key next. All right, so pause the video right here. All right, so once you're done, so you can check out your answer. So this is the answer key. I hope you have done all right. This is the answer key for the first practice. This is the answer key for the second practice. And if you have done it all right, way to go. And then if not, if you're having still any problems or troubles, or if you're confused anywhere, make sure you do question me in the comment section. I'll try to reply as soon as possible. So I hope this video was very helpful to you. And in the next video, we'll be covering up covalent compounds, naming for acids and bases. And of course, a lot other content is coming up related to chemistry, biology, and other major courses. And of course, extensive courses like AP and IB courses. So make sure you do stay tuned, subscribe the channel, like and share as much as you can, and support the channel as much. All right, thank you. Take care.